In this video, we're going to explore why texting and driving is bad by calculating how far you travel if you look down at your cell phone for 5 seconds while traveling at a constant speed of 35 miles per hour, then the distance you would travel if you looked up and needed to bring your car to a stop in order to avoid hitting a car in front of you or something that ran out into the road like an animal or a person. Now, to calculate the distance you travel while you're trying to come to a stop, we're going to make a few assumptions. The first thing we're going to assume is that you do not hit the object you're braking for. Another way to think about that is we're going to calculate the minimum distance that that object has to be away from your car between the time that you first notice it and your car comes to a stop. The second assumption is that the maximum rate at which your car can slow down is going to be 8 meters per second squared. And the last thing that we're going to assume is that your reaction time is going to be 0.75 seconds. That is, the time it takes between when you look up and see the braking car in front of you or the animal that runs out in front of your car and the time it takes for you to physically react to that stimulus is 0.75 seconds. Now, I'm using 0.75 seconds as our reaction time because the National Highway Traffic Safety Administration has done a lot of tests and discovered that the average adult driver has a reaction time of 0.75 seconds. Also, if you ever look up in a driver's ed manual, the stopping distances, they're all based on a reaction time of 0.75 seconds. Now, the first thing we should do is draw a diagram that represents what's going on within this problem. So if this represents our car, then we know that this car is going to be traveling in this direction with a constant velocity of 35 miles per hour. Now, 35 miles per hour works out to be about 15.65 meters per second. Remember, to use our kinematic equations, we need to be in SI units, the units of meters per second. Now, this car is going to be traveling in this direction at constant velocity for a total time of 5 seconds. Now, what we need to do, we need to calculate the distance that this car travels during that 5 seconds, and we're going to call this delta x1. And notice that I'm keeping track of the distance this car travels from the front of the car to the front of the car, the same point on the car. Then what's going to happen is the driver's going to look up and see that they're going to need to come to a stop. And so they're going to travel an additional distance, which we're going to call delta x2, which represents the distance that you travel before your brain has a chance to respond to the stimulus in front of you. That is, before your brain can react to a braking car or animal that's running into the road. Now, one of the things that you need to know is that you're moving in this direction at constant velocity during this time. Your body hasn't had a chance to physically apply the brake during this period of time. And so one of the things that you should remember is that the acceleration during this interval of time is going to be 0 meters per second squared. That is, you're not going to be slowing down during this interval of time. The other thing to keep in mind is that it takes 0.75 seconds for your brain to respond and physically apply the brake. And after your body has had a chance to react, the car keeps moving in the forward direction but begins to slow down. That is, it begins to decelerate. And so during this period of time, you're moving in this direction, so your velocity is going to be in this direction. You're going to start from an initial velocity of 15.65 meters per second. During this entire period of time over here, you're traveling at constant velocity. And then what happens is you're going to slow down and come to a final velocity of 0 meters per second. You're going to come to a stop. Now, the car is going to be accelerating in the opposite direction that the car is moving. And in this case, the acceleration is going to be negative 8 meters per second, or negative 8 meters per second squared. What we want to do here is we also want to calculate the distance that it takes for you to come to a stop, and in this case we're going to call this delta x3. Now, while you're applying the brake, we don't know how long it takes for you to come to a stop. So now that we've diagrammed this problem out, we're going to break it down into 3 separate problems. We're going to look at how far the car travels during this interval of time, then we're going to look at how far this car travels during this interval of time, then we're going to try to figure out how far this car travels while the driver is applying the brakes. So in this case, we're going to use our kinematic equation that says that the distance that this car travels, and this is going to be during the first interval of time, is going to be the initial velocity of the car times the time over which this car is traveling plus 1/2 the acceleration of the car times the time squared. Now, during the period of time when the driver is looking down at their cell phone, they're traveling at constant velocity, so the acceleration of the car is 0. So we can now say that the distance that this person travels while they're looking down at their cell phone is going to equal the initial velocity of their car times the time during which they're looking down at the cell phone. Now, for this part, we said that their initial velocity was 15.65 meters per second, and then we're going to multiply that by the time that they are distracted, in this case 5 seconds. And one of the things that you should see is this unit a second cancels out with this unit a second, and 15.65 times 5 works out to be 78.25 meters. And 78.25 meters works out to be about 256 feet. And to give you some perspective as to how far you travel while you look down at your cell phone for 5 seconds while you're traveling at 35 miles per hour, you travel about 3/4 of the length of a high school football field, which is 360 feet from goalpost to goalpost. Next, we're going to calculate the distance that you travel before your brain has a chance to physically respond to the stimulus of the car or object running out in front of your car. And in this case, we call this delta x2. And in this case, this is going to be the initial velocity at that point times the time plus 1/2 the acceleration times the time squared. The acceleration of your car is still 0. And so you're traveling with constant velocity during that interval of time. And so the distance that you travel is going to be equal to the initial velocity of the car times the time. And in this case, this is still 15.65 meters per second. But in this case, you're traveling at this velocity for only 0.75 seconds. And again, notice this second cancels out with this second, and then you take 15.56 and you multiply by 0.75 seconds. And when you do this, you get about 11.74 meters. So you travel an additional 11.74 meters before you have a chance to hit the brake. Now the last step is we want to calculate delta x3, the distance that you travel while you're slowing down. Now, like in the previous cases, we don't know what this distance is. We also don't know how long it takes for this car to slow down while it's braking. But we do know what the initial velocity of the car is. It's still 15.65 meters per second. The car has not slowed down since you look down at your cell phone. And we know that it's going to come to a stop once the car begins to brake, so its final velocity is going to be 0. And we also know how fast the car is slowing down. In this case, we're saying that it's going to slow down at -8 meters per second per second. And so to calculate the distance that this car travels, we really can't use this equation that we have in the two previous examples. So we can't calculate the distance by using the initial velocity times time plus 1/2 the acceleration times the time squared. And the reason we can't do that is because we don't know how long it takes for this car to come to a stop. So the kinematic equation that we're going to use is the final velocity squared equals the initial velocity of the car squared plus 2 times the acceleration times the distance over which this car is going to slow down. Now in this case, the final velocity of the car is going to be 0, and so we can rewrite this as 0 equals the initial velocity of the car squared plus 2 times the acceleration of the car times the distance that this car travels while it's slowing down. And we should subscript this as delta x3 because this is going to be the final distance that we're looking for. Now the next step is to take this term and put it over to the other side. So we're going to subtract the initial velocity of the car from both sides. What you do to one side of the equation, you have to do to the other. And what you should see is you get minus the initial velocity of the car squared equals 2 times the acceleration of the car times the distance that this car travels while it's slowing down. Now the last thing that we're going to do is we're going to divide both sides by 2 times the acceleration. What you do to one side, you have to do to the other. And what you should see is that this term cancels out with this term, and you get the distance that this car travels, this delta x3, while it's slowing down is going to equal minus the initial velocity of the car squared divided by 2 times the acceleration of the car, that is how fast this car is slowing down. In this case, this works out to be minus 15.65 meters per second quantity squared divided by 2 times -8 meters per second per second. And what you should see is that negative divided by a negative works out to be a positive number. This car is still moving in the positive x direction even though it's slowing down. And then when you take 15.65 meters per second and square the entire term and then divide it by 2 times 8, you get 15.3 meters. So the car travels an additional 15.3 meters while it's slowing down. So the total distance that this car travels is going to equal delta x1 plus delta x2 plus delta x3. So this is going to work out to be 78.25 meters plus 11.7 meters plus 15.3 meters, and this will give us the total distance that this car travels, which works out to be about 105.3 meters. So one of the reasons it's so bad to text and drive is because you travel a very great distance during the time that you're looking down at your cell phone, then you have to travel an additional distance before you have time to physically react to some object running out in front of your car. So that's some of the things that you should keep in mind if you decide to text and drive, especially as your velocity increases. That is, the faster you travel, the greater this distance is going to be, the greater this distance is going to be, and the greater this distance is going to be. Therefore, this distance will increase greatly.